Hey there, welcome back to the channel. Today, I want to talk just generally about how you go about building a custom solution or a custom device with .NET for an embedded type of project or an IoT project. For a project I'm working on, we want to measure vibration on machine tools. We want to do it in 3 axes, and so I've got these accelerometers. This accelerometer puts out 4 to 20 milliamps. So the question is, how can we do this 4 to 20 milliamp sensor at a vibration? We want to be able to detect up to, say, 50 kilohertz vibration. So we need to be able to sample 3 channels at 100 kilohertz due to the Nyquist cutoff to make sure that we can get a 50 kilohertz sample. So how do we create an application or a device that can sample 3 channels, and probably 4, we'll probably want acoustic as well, but let's say 3 channels at 100 kilohertz and still be able to display data and serve data up over something like a WebSocket. What I ended up doing was building some custom hardware. And so I'm going to go through this and kind of how the development happened on this and, the general pieces. First, I tried to run this on a Meadow F7 device. So this is the F7 Feather. This has a STM32 processor on it. This turned out to be able to collect data from a single channel at a rate that was fast enough, but it couldn't do anything else. So I had to move up to something with more horsepower. I then moved up to a Raspberry Pi, and I used a Raspberry Pi 4 here. The challenge with a Raspberry Pi 4 is it does not have an A to D on it, right? So we need an A to D in order to be able to take in this analog signal. The other challenge that I had was this does 4 to 20, and I need to be able to condition that signal from 4 to 20 into an input that is an analog for my microprocessor. Another challenge was I need to be able to filter that data. I want to get rid of spurious signals above 50 kilohertz. So I really need a 4 to 20 input that is filtered. That actually gets taken care of by this device here. Again, we don't have A to Ds on the Raspberry Pi 4 itself, but I do have a Raspberry Pi Pico, which does have A to Ds. It has 2 channels of A to D, and I need 4 channels of data, so I had to make provision for 2. So really what happens here is this signal comes in to this 4 to 20 filtered I/O piece, and I'll talk more about it in a minute. But basically, this takes that 4 to 20 and turns it into a 0 to 3.3 volt signal. That comes over into this Raspberry Pi Pico into one of its A to D channels. The Pico has a 2-core processor on it. So really what's happening is one core ingests this data as fast as it can and does FFTs on that data. It then takes the FFT output and transfers it to a memory block that is shared between the 2 cores. And then the second core of the processor takes that FFT output. So it's really just looking at frequency and magnitude of the buckets in the FFT, and it ships those out continuous stream over a serial port. That serial port is then connected over to the Raspberry Pi. So we've got 2 channels go into the Pico. The Pico is doing FFT on one core. It takes that data, passes it to the other core. That other core streams it over serial over to the Raspberry Pi. This is all written in C. And then the ingestion over here on the Raspberry Pi is written in C#. It's simply listening to 2 different serial ports for the FFT data, and it then stores it and both presents it and will, in the future, have it in a WebSocket. I haven't done that development yet. I still have a fair bit of hardware to do. But you can see what I end up with is I end up with this display, and this is an SPI display, so we're not using the HDMI capability of the device. Typical embedded project has a single app with a single user interface. I don't want a desktop. I don't want the user to be able to navigate around, things like that. This is actually running a headless OS, and it's using the Meadow Micro layout for the display. So you can see here, it's showing data. Right now, the data display is set up to refresh just once a second. There's no need to try to give all of the data as it's coming across. The display probably couldn't keep up, and a human eye can't watch it for any meaningful amount at that rate. But what we can do is we can verify that we're getting some data. Then we also have a graph view. You can see here, in the graph view has 3 dimensions. So we've got our X is a logarithmic frequency. Our Y is the magnitude of the signal. And so it's really just plotting those buckets that are the output from the FFT. And then the third dimension is the brightness of the color. So you can see there's some bright cyan and then darker blue. So when signals come in, they're plotted in this cyan, and then as they age out, they fade to a darker color. So that's our third dimension. So if I take this accelerometer and I move it, you can see that we get signals that are down in this lower frequency range. So you can see it moving around down here. So the overall solution, we have a C# application running on this Raspberry Pi 4 here, and it is using the Meadow stack from Wilderness Labs, using that for ingestion of the data as well as display. I have Raspberry Pi Pico with a C application running on both cores. And then over here, I have custom hardware that was built. In fact, this whole thing is custom. Now, my skill level allows me to design and lay out and have these built. But when it comes to more complex circuitry, such as this filtered 4 to 20, this was probably beyond my capability, certainly beyond my capability to make. I outsourced this to Wilderness Labs, so they designed this. So when you're looking at building a solution like this, you can leverage the knowledge that you have and the capabilities you have in-house with capabilities that other experts have. So what I've done is, again, we've got this was outsourced, then I built this board, this carrier board myself. Obviously, the Raspberry Pi Pico is an off-the-shelf. The Raspberry Pi 4 is off-the-shelf. I had to do the software to do the ingestion and the logic, but most of the input and driving this display was using libraries from Wilderness Labs. In my view, this is a classic example of a good use of .NET or something that actually requires real-time capability. So the real-time capability of this solution is written in C over here, but I would not want to try to do this rendering in C. So we transition from the real-time C stuff, transfer that data to the processor that is running .NET, and then over in .NET, I'm able to use all of the convenience and speed of development there in order to generate the application that allows me to provide user display on this HMI, as well as exfiltration of the data through something like a WebSocket. So that's it for today. I really just wanted to give you an overview of how I approach building something like this, a custom piece of hardware for a specialized application that is an IoT app that will be running .NET for the primary application. Thanks for watching.